Well, let's look at another famous system associated with free body diagrams and Newton's laws. This is the so-called Atwood machine. So an Atwood machine is a simple device. It's a pulley, and there is a couple of masses which hang over each of those pulleys. Let me see if I can do that a little bit better. Right, there's a rope or something like that, and on the end of each of these is a mass. And they're usually not the same. One's bigger than the other, or one's heavier than the other. Okay, so the first assumptions that we typically make are that the pulley is frictionless and the rope doesn't stretch. And so all that happens is we have the force due to the tension of the rope and the force due to gravity. Okay, so let's just draw those in briefly here. So gravity is going to pull this mass down. Let's give this thing a name. We'll call him number 1 and this one number 2. Okay? Gravity is also going to pull this one down. Now, there's a tension force, right, provided by the rope, which is going to go up this way. I'll call this, well, I'll give them names later. And then this one is going to go like so. Now, naturally, I've illustrated this as though mass number 2 is more massive than mass number 1. So we definitely expect the system to sort of like accelerate in this direction, right? Which means, or I mean the right-hand side is going to accelerate in that direction, which means the left-hand side is going to accelerate in that direction. So these are the ways the acceleration are going to go. The magnitude of them are going to be the same. The direction is different, although the direction is a little weird because they're attached by a pulley. It makes sense that the magnitude will be the same. They're attached by a string, right? So if this thing is going in the downward direction, if mass 2 is going in the downward direction, then mass 1 has to go in the upward direction. Okay, well, let's give these things some names. So this is going to be T2. I call it T2 because it's a tension. 2 because it's mass number 2. T1. And then we're going to have W1, the weight of object number 1, and W2. There's no other forces here. I mean, there's no wind blowing, there's no friction, and because we have a frictionless pulley and a weightless, massless pulley, we don't have to include that in the equations of motion for this system. So if I'm going to make a free body diagram, I actually have to make 2 free body diagrams. I have to make one of them for mass number 1 and one of them for mass number 2. Okay, so I'm going to put this in here. T1, W1, and the free body diagram for mass number 2. I'm going to have W2 and T2. Okay, so we have now the free body diagrams. Let's be clear about it. The free body diagrams are the things over here. Okay. They are simplified dramatically. This allows us to work on the problem because we can solve Newton's laws for this object and this object somewhat independently. Okay, there are some constraints though. Okay, it turns out that T1 and T2 are equal in magnitude. Okay, T1 is equal to T2 in magnitude. So whatever force that object number 2 applies to the rope, pulling on the rope, object number 1 feels pulling in the other direction. Okay, there's the pulley there, so there's a problem with the directions that we need to make sure that we know about. But still that magnitude is the same. And I mentioned this other case before, which is that the magnitude of A1 is equal to the magnitude of A2. So these are two constraints that we can work with when solving the problem. It's the way that we connect these two objects together, but we can write Newton's laws separately for each one. So let me just quickly do that. So that F1 is going to be equal to T1 minus W1, and that's going to be equal to M1 A1. Okay? And similarly, that F2 is going to be equal to T2 minus W2 is going to be equal to M2 A2. So these are my equations of motion right there. And I have the constraints that I already illustrated here. And so now that I've set this up, I can solve each of these two equations separately, simultaneously with the constraints.